Okay, last time we have been discussing about the torque free rotation of a rigid body. So, we derived the relationship that psi dot this equal to I 0 phi dot divided by I minus I 0 times cos theta. So, today we will discuss about the attitude dynamics, the remaining topic, and this is the last lecture on attitude dynamics, and thereafter the remaining time we will devote to the propulsion. So, we derived this equation where psi dot and phi dot, these are the Euler rates or Euler angle rates. So, we can write this as phi dot divided by I by I 0 minus 1 cos theta. Now, if I 0 is greater than I, so for this case we can write psi dot equal to minus phi dot divided by 1 minus I by I 0 cos theta. Now, the quantity 1 minus I by I 0 cos theta, this will be always less than 1, and okay, we can see that I is always a positive quantity, I 0 is always a positive quantity, and what we are assuming that I is less than I 0. So, therefore, this is going to be smaller than 1. So, this quantity will be always positive, and theta always it will lie between, say the theta we are measuring from the vertical. Okay, so, it will lie between minus pi by 2 and plus pi by 2. So, therefore, this is going to be always positive, okay, and this is less than 1, this quantity magnitude of this will be less than 1. So, therefore, here we can write cos theta is lying between 0 and 1, okay, as theta is bound to lie between on this end we are not putting the equality sign, which will be quite obvious very soon. So, this quantity will basically turn out to be between 0 and 1, and therefore, what it implies that psi dot is opposite in direction to opposite in sign to phi dot. Here we write this equation as a 1, this is 1 and this is 2. So, from equation 2, psi dot is opposite in sign to phi dot. Also, we can conclude that psi dot magnitude, now this quantity is less than 1, and therefore, the quantity 1 by 1 minus I by I 0 cos theta, this magnitude will be greater than 1. Okay, so, for this simply implies that psi dot magnitude will be greater than phi dot magnitude. In the motion right now we have considered. So, here the we find that psi dot is opposite in sign to the phi dot. So, this signifies this is the negative sign before the relationship between psi dot and phi dot. So, this signifies phi dot opposite sign signifies the retrograde motion. So, if your say if the this is the vector, suppose psi dot, this is the direction of the psi dot, then phi dot will be opposite in sign. So, that simply implies that this rotation is being shown anti-clockwise. So, phi dot is bound to be clockwise. So, phi dot we can show as with negative sign. Okay, so, they are basically not in the same direction, because the spin vector for the spin about a particular x, we decide its orientation, its a direction according to the way it is spinning. If it is spinning anti-clockwise, means its a direction is like this. If it is spinning and in the clockwise direction, so we put the direction downward. So, according to the same convention we have shown here. So, now considering with considering this convention, okay. So, if the this is psi dot, and say if this is the phi dot vector, this will be omega, and this is our retrograde motion, and this we have written for I 0 greater than I. And already we have described the body cones for the retrograde and the prograde motion. Now, again taking the equation number 1 here, now take the case now taking the case when I is greater than I 0. So, if this is the case, then this simply implies that psi dot and phi dot both have same sign, because this quantity is positive. Okay. This quantity becomes positive and this quantity is positive. Okay. So, therefore, the sign of psi dot and the phi dot, it is the same, and this is called prograde or retrograde motion, or also we can term this as the retrograde precession. Retrograde precession, and this we write as prograde precession, or also this is called direct. Okay. Direct precession, direct precession. Okay. Moreover, from this equation number 1, we can observe that if theta tends to pi by 2, okay, means this quantity will tend to 0, okay, and at that time psi dot becomes infinite. Okay. If this tends to 0, so this quantity will tend to the whole quantity on the right hand side will tend to infinity. So, implying that psi dot becomes infinite. Okay. So, means the precession rate, once it becomes infinite, only then you will have the nutation angle. This theta is signifying the nutation angle. So, we can write here theta is equal to pi by 2, or as theta tends to pi by 2, signifying 90-degree nutation angle, and this leads to infinite precession rate, and physically this is not possible, obviously. Okay. Okay. So, in this case what we can write, the omega is psi dot, this is a vector, plus phi dot vector plus theta dot vector. Okay. And for the torque free motion, for the torque free motion, we have already proved that theta dot equal to 0. Okay. So, this implies omega is equal to psi dot plus phi dot, and this is what we have shown in this figure. So, this is the retrograde precession, and now we can add one more figure. So, we can show it on the same slide maybe. This is your psi dot vector, okay, and phi dot vector. So, let us say this is your phi dot vector. So, omega dot vector will point in this direction. Omega vector will be pointing here, not omega dot. Okay, and this is our prograde or direct precession. Okay, so, this completes our discussion of the rotation. Now, we come to the stability part. So, our question is here whether a torque free rotation of a rigid body is stable. Okay, so, obviously, in this case we have started with the case of a cylinder. So, we will continue with that. So, we consider here a rigid body. So, in general we can choose any body. So, we have the case of cylinder already. So, either we can take the case of a cylinder or either we can take any rigid body, but let us consider the motion to be about any of the principal x and the body x is to be aligned with the principal x of moment of inertia. So, here principal x, this implies principal x of moment of inertia, it is the same thing. Okay, and we want to study the stability of this body. Okay, so, to start with, we have the Euler's dynamical equation we have already written. So, when the off diagonal terms are 0, so we have this equation earlier developed I 2 minus I 3 this times omega 2 omega 3. Similarly, we can write omega I 2 times omega 2 dot Okay, so, we have these equations. Now, in these equations we can see that if omega 1 and omega 2 equal to 0. So, this implies I 1 times omega 1 dot this is equal to 0 from equation 3. Okay, so, this implies omega 1 this is a constant. Similarly, if omega 1 and omega 3, so here let us put like omega 2 and we have written the wrong thing. Let us correct this here omega 2 and this is omega 3, omega 2, omega 1 and omega 3, omega 3, omega 1 and omega 2. So, if we have omega 1 and omega 3, these are 0, so that is omega 1 equal to 0 and omega 3 equal to 0. Okay. So, at that time we will have I 1 times omega 1 dot this is equal to 0 from equation 3 and this implies omega 1 is a constant. Similarly, if omega 1 and omega 3 are 0, that is omega 1 equal to 0, omega 3 equal to 0. So, this implies I 2 times omega 2 dot this is equal to 0, okay, implying that omega 2 this is a constant. Similarly, if omega 1 equal to 0 and omega 2 equal to 0, then we will have omega 3 times I 3 times omega 3 dot equal to 0, implying that omega 3 this is a constant. So, the conclusion is that it is possible it is possible that body can rotate about any of the principal x, provided that angular velocity along the other two principal x is 0. Okay, so, if it happens, then it is a possible that it will the body can rotate, and that is what we set the question. So, we assume that here let us consider that the motion to be about any of the principal x, okay, not about all the principal x. Okay, obviously, any angular velocity vector can be broken along all the body x. So, the body x we can choose along the principal x. So, in that case it implies that the motion is taking place along all the principal x. So, that situation we are avoiding, we have taken a simple case where the body is chosen to rotate about any of the principal x. So, now let us consider body is rotated body is rotating about the E1 x. Okay, if you remember, we choose the body like this. So, this was your E3 cap here in this direction, and this was E2 cap, and here it was E1 cap. So, these are the unit vectors in the E1, E2 and E3 directions. So, let us consider that the body is rotating about the E1 x, or simply we can put as a E1 here notation, because the mostly notation we choose as for the reference as E1, E2 and E3, while these are indicating the unit vectors. Okay, so, we will write here that omega 1 equal to omega 0 and omega 2 omega 3 this is equal to 0. Okay, so, with this assumption, let us perturb the angular motion of this body. Okay, so, what we are assuming that omega 2 and omega 3 they are 0. Let the perturbation in angular velocity components along E1, E2, E3 directions or along the E1, E2, E3 access B epsilon alpha beta. Okay, so, if we are taking this omega 2, omega 3, omega and all of them to be 0. Similarly, here the quantity omega 3 is 0, here in this place also omega 2 is 0 except omega 1. So, what we get I 1 times omega 1 dot, you can write this as I 2 minus I 3 times omega 2 plus, and we are assuming that there is the perturbation we are giving is alpha, beta and gamma. So, these are correspondingly given to, in the omega 2 we are giving alpha, and in the omega 3 we are giving the perturbation beta. Omega 2 is equal to omega 3 equal to 0. Okay, this we have already assumed, and moreover we assume that alpha beta are small. Okay. So, this implies I 1 times omega 1 dot is equal to I 2 minus I 3 times alpha beta, because omega 2 omega 3 are 0, and the quantity which is alpha beta, this is a second order term, and therefore, this will be nearly equal to 0. Okay. Similarly, I 2 times omega 2 dot plus alpha dot, this will be I 3 minus I 1 times omega 1 plus epsilon. This is the perturbation in omega 1, and in omega 3 we put as omega 3 plus epsilon alpha, and gamma we have taken beta. So, here omega 3 is 0. So, this gets reduced to I 3 minus I 1 times omega 3 omega 3 plus epsilon times beta. Now, we have already chosen that. Okay, one thing here in this equation, moreover we can write, as we have written here in this place, on this side the perturbation we have given to be epsilon. So, here we can write the epsilon dot. So, instead of writing in this way, now omega 1 we have assumed to be constant. Okay, so, omega 1 we have written as omega 0. So, derivative of this quantity we can set it to 0, and so omega 1 dot will be 0, and simply we can write I 1 times epsilon dot. Okay, so, this is our equation number 6, and here in this place similarly omega 2 we have assumed to be 0. So, this quantity vanishes, leaving us with I 2 times alpha dot, this is equal to I 3 minus I 1 times, and omega 3 is already 0. So, this will vanish. Writing afresh the whole thing. I 2 minus I 3 times omega 2 omega 3. Okay. So, this implies I 1 times okay. Let us perturb this by epsilon. So, this becomes epsilon dot and omega 2 plus alpha and omega 3 plus beta. Omega 2 this is equal to 0, omega 3 this is equal to 0. So, we have I 2 minus I 3 times alpha times beta, and this is a second order quantity as we have stated earlier, a second order quantity, or this magnitude of is of second order, because both are small. So, the product will be further small. So, this quantity we can set it to 0. So, this simply implies I 1 times, and moreover this quantity is 0. Okay. And this will write as the equation number 6. Similarly, we have I 2 times omega 2 dot, this is equal to I 3 minus I 1 times. Okay, here I 3 minus I 1 times omega 3 plus omega 3 plus the perturbation we are giving as beta. Okay, we wrongly copied here. So, I cancel this page. This is omega 3 plus beta times omega 1 plus epsilon. Now, omega 2 dot this will be 0, but the perturbation we can write here, but let us add the perturbation here in this place, omega 2 dot plus alpha dot, this is equal to. Okay, so, from here we have omega 2, this quantity is again omega 2 dot 0. So, I 2 times alpha dot, this becomes I 3 minus I 1, omega 3 this we have set to 0. Okay. Beta we can multiply here, omega 1 we have set as omega 0. So, this is omega 0 and times beta plus epsilon times beta. This quantity is small. Okay. So, neglected. So, this implies I 2 times alpha dot, this is equal to I 3 minus alpha times omega 0 beta, and this is our equation number 7. Okay, similarly, I 3 times omega 3 dot we have written earlier. So, omega 3 with this we give the perturbation beta. So, this becomes I 3 times omega 3 plus beta dot, this will be equal to I 1 minus I 2 times omega 1 plus epsilon and then omega 2 plus alpha. This quantity is 0, beta dot we get here from this place. So, I 3 times beta dot, this is equal to I 1 minus I 2, and if you look into this. So, we get here omega 1 which is omega 0, omega 2 this quantity is 0. Okay, so, this we can cancel from this place. So, this becomes omega 0 times alpha plus epsilon times alpha. Again this quantity is a small. Okay, so, we drop it out and what we get is I 3 beta dot equals to I 1 minus I 2 times omega 0 alpha. This is our equation number 8. Now, equation number 7 and 8 as we can see from this place. Okay. This is our equation number 7. This is written in terms of on the left hand side the rate of alpha and right hand side beta is appearing. Similarly, here we have the beta dot and on the right hand side alpha is appearing. So, this is basically coupled equation. Okay, so, this simply implies that one motion will be affecting the other motion. Okay, so, therefore, now we can differentiate the equation number 7. So, differentiating equation 7 and 8. So, what we get I 2 times alpha double dot, this is equal to I 3 minus I 1 times omega 0 times beta dot. Now, put beta dot from, let us put this as equation number 9, from equation 8 into equation 9. Okay. So, this will imply I 2 times alpha double dot equal to I 3 minus I 1 times, and from here we have the beta dot available. So, this is I 1 minus I 2 times omega 0 alpha. Okay, this we can write as, we can bring it on the left hand side and can be written as I 1 minus I 3 times I 1 minus I 2, okay, times omega 0 square times alpha, this is equal to 0. This is our equation number 10. Okay. Similarly, for if we differentiate the equation number 8, so differentiating equation 8, we get I 3 times beta double dot omega 0 times alpha dot. Okay. Now, alpha dot we have already available in equation number 7. Okay. So, this is our alpha dot present here. So, we insert this. So, inserting alpha dot from equation 7, this we write as equation number 11 into equation 11. So, this gives us I 3 times beta double dot equal to I 1 minus I 2 Okay, here we have missed one term, we put here the term I 1 minus I 2, and because we inserted for beta dot and beta dot we have the multiplied by I 3. So, we put here I 3 divided by I 3 and this is divided by I 3. So, for now we are inserting for alpha dot here in this place, and in the alpha dot equation we have I 2 present here. Okay. So, we divide it by I 2. Okay. So, with this equation let us further simplify, and this can be written as alpha double dot plus I 1 minus I 3 times I 1 minus I 2 divided by I 2 times I 3 times omega 0 square times alpha equal to 0, and we will name this as equation number 10. Okay. So, this implies beta double dot equal to I 1 minus, or we can add it, bring it the whole thing on the left hand side, omega 0 square, and this beta is missing in this place. So, we put beta, and this is our equation number 12. Now, from the equation 10 and 12, these are the two equations we have got. We can see that this equation is a simple harmonic motion equation, provided the quantity I 1 minus I 3 times I 1 minus I 2, this is greater than 0. Okay. Otherwise, if you have a, if this quantity is less than 0, so obviously this will not result in a simple harmonic motion equation, but it will have two real roots, and one of them will be negative, and that will lead to the unstable solution. So, what we are looking into the stability of this motion, whether this motion is rotational motion is stable or not. So, if now we can write here, if I 1 is greater than I 3 and I 1 is greater than I 2, okay, then quantity I 1 minus I 3 times I 1 minus I 2 divided by I 2 I 3 times omega 0 square, this will be greater than 0. Okay. So, let us put this quantity as k. So, if we write it in this way, so alpha double dot we can write as k times alpha equal to 0, and similarly we can write for beta double dot equal to k times beta double dot plus k times beta equal to 0. Okay. Now, for a stable solution, k must be greater than 0. Okay. As we have shown here, this quantity must be greater than 0, and that will be satisfied if this quantity is greater than 0, or I 1 is less than I 3 and I 2 is I 1 is less than I 2. So, what does it say? Okay. This implies that if the rotation is taking place about the maximum moment of inertia or the measure moment of inertia x or the minor moment of inertia x, then the motion will be stable. About any intermediate x, the motion will be unstable. Okay, so we have two conclusions. This was our conclusion number A and this is conclusion number B, that I1 which is the we have chosen as the axis of rotation. So, this should be I1 is greater than I3 and I1 is greater than I2, implying that this is the measure axis of inertia. So, this is measure axis of inertia is axis of rotation. And what does this implies? This implies that I1 is less than I3 and also I1 is less than I2. So, we have only 3 moment of inertia x. So, the I1 is less than both of them, okay, I2 and I3, implying that now the motion is about minor axis of inertia. Okay, so, if it takes place, the rotational motion is taking place either about the major axis of inertia or the minor of axis of inertia, the motion is going to be stable, otherwise it will be unstable. Okay, now we have done the stability part. Now, we can look into one very important conclusion, and that we can derive based on the energy results, and this is not a very rigorous treatment, but we are going to do a something ad hoc treatment. So, let us say we know that the rotational kinetic energy of a rigid body can be written as, let us say, T rotational, this is equal to 1 by 2 times omega tilde transpose times I, or we can remove this omega indicating these are the vectors and matrix. Okay, so, here in this case we have omega 1 by 2, omega transpose will be omega 1 which we are putting as omega 0, and rest we are omega 2 omega 3 we are putting as 0. Moment of inertia I 1 I 2 I 3, the off diagonal terms being 0, and omega here again omega 0 0 0. Okay. So, this implies omega 0 0 and multiply this will be I 1 times omega 0. So, this gives you 1 by 2 times I 1 times omega 0 square. So, this is the rotational energy of a rigid body. Now, this T r can be written as I 1 square times omega 0 square by I 1 1 by 2, and we know that if the rotation is taking a place about a particular x, earlier if you remember that the h vector we wrote as h 1 times E 1 plus h 2 times E 2 plus h 3 times E 3, where h 1 was I 1 times omega 1, this was I 2 times omega 2 and I 3 times omega 3 E 3 cap. Okay. While assuming the off diagonal terms to be 0. Okay, that is the rotation taking place about the principal moment of inertia x. Now, if omega 2 omega 3 these are 0. Okay, so, this simply boils down to omega I 1 times omega 1 E 1 cap. Okay. And this is nothing but I 1 times, in our case I 0 times E 1 cap. Okay. So, the magnitude wise we can write h is equal to I 1 times omega 0. So, till now we calculated this T r equal to h square by 2 I 1. So, in general we can write the T, the rotational kinetic energy, this is equal to h square by 2 I. So, now we can have various situation in which, let us say T we write as minor T minor, this is equal to h square by 2 I minor, and similarly we write T major, this is equal to h square by 2 I major. Now, until unless the external torque is acting, the T on the left hand side we are starting with certain value of T minor, suppose. Okay. Now, until unless the external torque is acting, h will be constant, this will remain constant, and also suppose in the beginning with the for whatever the value of the h, we had the T minor here. So, this we start with certain value. So, the starting value is given. So, h is a constant if it is torque free situation. Now, there are situations in which this rotational kinetic energy it can die out. Okay. So, we can have some vibrating part mounted on the satellite. Okay, suppose this is our satellite. So, we can have antenna mounted on this satellite. So, this antenna it is a flexible and it is called turnstile antenna. So, if this vibrates, okay, so this will absorb energy. So, your it is a torque free situation. So, this part is constant. Okay. Now, the energy, the rotational energy will be absorbed continuously, because this antenna may be oscillating. If inside the satellite there are some moving parts or some damper is there. So, that may also act to absorb the energy of the satellite, rotational energy of the satellite. So, this energy will start decaying. Now, this part is constant. So, this can be compensated only if this part changes. Okay. So, in this case what happens? So, if this is decreasing, kinetic energy is decreasing. So, this will happen only if I increases. So, I minor, this will get changed to I major, means that if the satellite is rotating about the minor principal axis of inertia. So, it will slowly deviate from this, motion will get perturbed, start with the satellite will start tumbling, and thereafter it will resort to rotation about the major principal axis of inertia. This is major. Okay. While if we look into this situation, so here there is no scope of change of this I major. Here there was a scope that I minor can change to I major, but here there is no scope. So, we say that if the satellite is rotating about the, if the satellite is rotating about the major principal axis of inertia, then the satellite rotation is stable. Okay. So, we concluded earlier theoretically that if the satellite is either rotating about the minor axis or the major axis, so the rotational motion will be stable. But we see that the rotationally the energy wise this part is not stable, because as the energy dies out, the satellite deviates from the minor axis and comes to the major axis rotation. Okay. So, therefore, the satellite will remain stable only if it is rotated about the major moment of inertia, not about the minor one, major moment of inertia x. So, we have completed this part. Now, to quote as an example, this American satellite Explorer 1. So, after the launch, within few hours it has started tumbling. Within few hours it has started tumbling, and this tumbling was because of the presence of this turnstile antenna. So, because of this antenna, the satellite this vibration of this as it vibrates. So, it will absorb the energy, the vibration of this, some energy will get dissipated as the heat. Okay. So, because of the absorption of the energy, so slowly it has started, it was set initially in the its rotation was set on the minor principal axis. So, as this vibration has started, so energy has started getting dissipated. So, it moved from the minor principal axis to the major principal axis, and therefore, in this case the satellite gets lost. Okay. If you do not have the control system on board the satellite, then you cannot restore the orientation of the satellite again. So, say if you have launched a satellite which was put by using just the rotation, it was rotationally stabilized and you did not do anything for this. Okay. Now, you do not have control inside to change its orientation. So, you will find that this satellite, it has changed the orientation and its functionality is lost. So, therefore, the attitude control is a necessary part to reorient the satellite. So, anything can go with the satellite, some unforeseen can also be there. So, even if you have not designed for that those unforeseen things, but if your controls are present, then you will be able to reorient the satellite, okay, and restore its functionality. So, we stop here, and the next lecture we will start with the propulsion. Thank you very much.